Welcome to our second episode of Behind the Numbers podcast. This week we were honored to welcome Dr. Michael Hill, one of the top stroke researchers in the world. He is a professor and researcher out of the University of Calgary and director of the Calgary Stroke Unit. Dr. Hill tells us about his educational background, shout out to U Ottawa Med School, before diving into the details of his work on the ESCAPE trial, which was a defining moment in medicine due to its overwhelming positive results. This trial was one of the first to show that endovascular therapy for ischemic strokes could cut the death rate in half, as well as completely redefined our standard of care treatment. After that, we spoke about the promising results of his follow-up trial, ESCAPE NA1, and he gave us a little sneak peek at what he has planning next. This was an awesome episode to record, and I hope you enjoy listening to it just as much. Awesome. So first I was just hoping you could start off by telling us about your background, your education, how you kind of got to where you are now as a professor, physician, epidemiologist, director of a stroke unit, and all that.
Well, I did medical school at the University of Ottawa, so that was the best start, perhaps.
Yes.
Right? No. So I guess, things evolve in one's career, right? And often it's opportunistic in how things go. So after I did medicine, from the perspective of what happened to me over time, so I did medical school in Ottawa, and around the same time, my wife and I, or my fiance at the time, we decided we were going to stay in Ottawa. So I did medicine and internal medicine in Ottawa, and then I went on and did neurology in Toronto. And after that, I came to Calgary, and I've been in Calgary ever since that time. So, the evolution of what happened to me followed along. Just the way that career paths do. Often, it's opportunities that are presented in front of you, and you have to decide, okay, is this good for me or not? And this is the path that I ended up going down. I think when I was in Ottawa, it was clear at the time to me anyway that I wanted to do clinical research.
Mhm.
So the decisions that I took after that were really designed to follow that pathway. And I was, in terms of in what subject, then neurology was the one that interested me the most, and so that's why I ended up pursuing neurology, and then stroke was there were two things about stroke. The two reasons that I ended up choosing, neurology and stroke really were that at the time, was that the evolution of new therapies for stroke, and stroke's a major illness, right? And
Yeah.
multiple people get stroke. So the evolution that there might be an acute treatment meant that there was going to be opportunity to do clinical research. That's where the things started to come together.
And you did your master's in epidemiology at University of Calgary, correct?
So when I came to Calgary, I started with a stroke fellowship, and I did a master's degree in epi at the same time.
Okay, great.
That's about getting the right training, right, to be able to do clinical research.
And now, so because we have sort of a broad range of listeners from like undergraduate students all the way to the scientists, can you just briefly explain what a stroke is for those undergrads who are listening?
Yeah, sure. So broadly, we think of stroke in two types, right? One is ischemic and one is hemorrhage. So it's a stroke in that sense is a vascular event that affects the brain. Now, the ischemic type is much more common than hemorrhage, so about sixfold more common. 85% of strokes are of the ischemic type, blocked artery type. So why does an artery get blocked? Cholesterol plaque, a clot from the heart. Lots of different reasons why arteries can get blocked, and then what happens is that the brain is deprived of nutrients from blood, right? Glucose, oxygen, that kind of, and it suffers damage. That's what happens in stroke. The hemorrhage type, it's the blood that causes the damage.
And so when you were sort of getting into stroke research at first, at the time, the main standard of care was TPA, which is the clot busting medicine, correct?
Right, Gabrielle. So that was just evolving as a therapy, right? And
Okay.
yeah, that's right. So that was a new thing, and it was obvious that, well, it worked, and then there would need to be a lot of study to figure out, well, what are the right patients and that kind of thing. So this is where,
Because it can't be used for everyone, I believe, right?
That's right. So it only applies to ischemic stroke, and then it only applies to a subset of those ischemic strokes.
And then was it for that you, now moving into your ESCAPE trial, that you wanted to look at EVT as a therapy because TPA can't be used for everybody?
That's partly true. So, but I think that the biggest issue was that it didn't work all that well for some patients, right? So it's true that alteplase or TPA clearly works, and it increases the proportion of patients who have good outcomes by opening up arteries. So think of it, for those people listening, think of it as like Drano, right? So
Yeah.
alteplase is biological Drano. It's going to clear out a clogged artery, but it works only in some people and in some circumstances. And when you have a really large artery that's blocked, it doesn't work very well. So actually, the main driving force to getting into endovascular therapy, a really large artery block, there isn't an alternative. The TPA doesn't work well. And then sure, it's quite true that people with blocked arteries who have reasons that they can't get TPA, for example, they're on a blood thinner or they had recent surgery or something like that, then yeah, you need another therapy. So both of those things were key considerations.
And then moving into your ESCAPE trial, can you just give a little synopsis of what your aims were with that going into it?
Okay, well, we did a lot of work in Calgary on this concept of endovascular therapy. So this is about either delivering chemical treatments or using devices, retrievable stents, or aspiration catheters, where you essentially are sucking out a clot, but doing locally removing the blockage from a blocked artery. So you have to put a catheter in the femoral artery in the groin, and sort of snake it up under radiographic guidance up into the head. And this technique had been used to treat aneurysms. So there was a way of putting coils in aneurysms. So there was available technology to get to the clot. There weren't very good technologies for extracting the clot. But we started by giving intra-arterial therapy, and lots of people were doing it around the world. And then we were involved in a number of clinical trials, which were all essentially failing. We thought we were planning this in the 2013, I guess, or 2012, was that we could do better than what was already being done. And around the same time, there were new devices coming out, and so we organized a trial to test the idea that opening up these big arteries for the people with big blocked arteries would make people better. And I think as we suspected, it was a profound success, right? We all thought this was a good idea, and there were certainly good reasons to believe biologically that this was the way to do, if you selected the patient properly, and if you acted quickly, and if you actually got the arteries open. So the bit about executing the trial better was about doing those things, right? Selecting people properly, using the right imaging, right? Using the right technology, and
so was that the selection and the speed to treatment, do you think that was the difference then? Because there were a few trials that didn't show any positive results beforehand. So was that the difference, sort of the newly innovative technology?
Well, I think so. I mean, I think certainly the companies that make the technology said, "Oh, it's all tech." Actually, the issue is that if you don't select the right people and you don't do it fast enough, tech is useless, right? So, you're enabling the success of the technology by selecting patients properly, using imaging, and then by acting really, really fast. So those three things had to come, come together to make it work. And I guess that's really what we saw in ESCAPE. And to be fair, ESCAPE we were certainly the fastest of all the major trials there's been several trials. So for people understanding, ESCAPE trial was the Canadian effort, but involved global centers, other centers in Europe and South Korea, etc. But the biggest thing I would say about that trial is we were way faster than everybody else. It showed, right? We had a mortality benefit, and we showed lots of things about the benefit of acting really quickly.
Yeah, mortality went down by 50%, correct? I saw that. Yeah, which is very impressive and I think the positive
Right.
yeah.
When you have That's right. That's right. And I think one of the things about mortality is, and I mean, it's always in stroke, we always worry about the idea that what if we save someone's life only to leave them badly disabled? But on the whole, in stroke, if you have a reduction in mortality, you also have a reduction. And the great benefit was that we had a large proportion of people were, instead of being disabled, they were at home, right? They were able to
Yeah.
go home, and actually, it's been good, right? And I think it's made a big difference to stroke overall. So even yours in Ottawa, you there's a visible difference to what happens on the stroke unit. Less people are going along.
Yeah.
Yeah, it's been a pretty amazing.
Yeah, and like you said, there was such great success. And I saw a video that you did with Alberta Innovation where you said you were out for coffee when you heard about the Mr. Clean results of their study. When you started the ESCAPE trial, did you know, like, have an inkling that it was going to be the success it was? Or was it that moment where you got the phone call where you realized you're sitting on this gold mine of research, let's say?
Well, I mean, I think, not to be,
Mhm.
when you design a randomized trial, in which you I mean, the hypothesis was that
Mhm.
endovascular therapy
Yeah.
was going to be better, right? And so what we didn't really know was how much. I think we were all pretty certain that if we did it well enough, we would, we would find an effect, but we just didn't know that it was going to be as large an effect as it was. We had no idea we were
Yeah.
saving lives, right? I had no idea about that part. So I think that the magnitude of the effect was indeed surprising that it was so large. Um, yeah, so we certainly did think we were going to show.
Yeah, and it was because of that magnitude. I know you guys wrapped up a bit earlier because of the positive outcomes, and there were 3 other studies at the time that your team, their 3 teams, the Mr. Clean team, sort of pooled together for the HERMES collaboration to bring all the data together. Was that formed after you had wrapped it up and you guys published your results, realized there were other teams doing the same thing, or did you already know all of you were doing that and sort of collaborated as soon as the Mr. Clean results came out?
No, we started after we published and Mr. Clean published. They were in February, we were in March, and then we started to talk to
Yeah.
everybody else to say, listen, let's get everyone together. So we organized that collaboration from Calgary, and one of the things that happens statistically, right, is that if you have a large effect size, large magnitude of benefit in this case, you actually don't need very many patients to show that outcome. So, one of the driving principles behind trying to pull all the data together was that we all had, relatively speaking, smaller
Mhm.
trials. So we would have very poor power to look at some of these important subgroups of patients,
Yeah.
whether they were, older patients, for example, or men versus women, or patients with atrial fibrillation or not, that kind of thing. And the other thing we wanted to do was we wanted to standardize the imaging interpretation. As remember, I said there were sort of 3 pillars of why
Yeah.
we had success. One of the key ones was imaging, and so we were really really keen that we had all the imaging interpreted in the same way. That was really important.
And then moving from the ESCAPE trial, the next one sort of was the ESCAPE NA1 that had neranotide. Am I saying that correctly?
Yeah.
Okay.
Right.
And so overall, I think that one wasn't overall positive in terms of outcomes, but then there was a certain subgroup that did show really positive outcomes with that.
I mean, it's been an interesting story. We've been working with a group in Toronto who have developed this compound for a long time, more than a decade, more than 50 years.
Wow.
And what seemed to be the natural thing was that once the ESCAPE trial was published, that it made a lot of sense for us to look at this compound in this setting. And the main reason is that in most of the stroke literature in the past, in animal models, they've always used what's called an ischemia reperfusion model. you block an artery and then you wait some time, open the artery. And in that setting, various molecules
Mhm.
effective in helping getting better outcomes and so-called neuroprotecting the brain, right? So that's what NA1 is
Yeah.
thought to do. Function is a so-called neuroprotectant, and now it has this name, as you point out, neurinotide. And so it made a lot of sense for us to now look at it in this model because in ESCAPE and the other, anyway, with endovascular therapy, we now had a clear ischemia reperfusion model in the human. And so that's what that was about. Now, the findings are intriguing, and they relate to a pharmacological interaction between alteplase. And it basically looks at it's both a qualitative and a quantitative interaction, which means that if you have alteplase on board, it seems to nullify NA1, and if you don't have alteplase, then quite a large effect size. So it seems to work, right, in this population. And we have a lot of material that's unpublished at this point, proprietary, but we do have quite a lot of data on the pharmacology side to support the idea that this is in fact true, right? That the biology is such that alteplase results in cleavage of NA1. Don't have alteplase on board or any thrombolytics, then you. So this is we did predict that this might be a problem. So we did stratify the trial. So in fact, ESCAPE NA1 trial actually has two strata set up, so they're actually randomized underneath each strata. So it's pretty powerful evidence that there's something there. We think it means that neuroprotection is possible, and we're actually just about to start the next trial, which is going to be called ESCAPE Next. Okay. And it will be, and the next starts for excluding thrombolysis, right? Neurinotide excluding thrombolysis. So we'll look at the population of patients who are not getting thrombolysis, and essentially try to duplicate this finding, prove it, and if that turns out to be the case, then I think that seals it that it's true, and we'll try to get the drug licensed for use.
That would be amazing if that ends up showing sort of the same positive results as this one.
We hope so. I mean, obviously, always in clinical trials like this, there's an opportunity or a possibility that what you found is finding. But absolutely, we're hopeful that duplicate those.
I think I saw too that there's been almost over 1,000 attempts at making something like neurinotide. So it's a long time coming if it does have success.
Yeah. No, you're right, Gabs, and that is quite true, Gabby. Somebody did it. I can't remember who did it. It was Donnan in Australia. I think his group, they looked at it and they showed that there's been over 1,000 molecules have been tested. Only about 10% ever made it to human trials. But still, if there's been 100 drugs that made it to human trials and none have been effective, I think a lot of it has to do with the model, right? So I hope that what this means is that there is another therapeutic area, neurology, right, where we can actually intervene. But it seems to be that it's now, another condition of it being effective is you got to get the arteries open to establish reperfusion.
Yeah. Well, that sounds promising. And so other than ESCAPE Next, then has coming back to right now, has this pandemic at all affected your ability to do that research, or are you guys doing okay in Calgary?
Oh yeah, no, for sure. I think we're in the middle of starting up this trial, and lots of things have been because of COVID-19. And then I think one worry is that all of the patients or processes in hospitals have been changed and delayed. And time delays are a big problem for
us. Because like you said, that's one of the things for success is
fast. And so if we have to delay because we don't know if they got COVID, so that everybody can put on their protective gear and deal with the patient. So it's obviously it's a necessary thing. There's no way around it. But it's going to change. It has already changed the way stroke.
Speaking of time delays, is it true that I saw every minute that, say, your artery is blocked, you'll lose like 2 million neurons or something like that.
Yeah, that's an average,
Yeah.
an estimate. That's right. Yeah, 2 million neurons, 12 kilometers of axons, and 14 billion synapses.
Which just shows why the time
Yeah,
delays are so crucial.
Yeah, so we all have to move very
Yeah.
quickly, right? We try really hard to treat people quickly. Everyone knows this, right? You have to run from your car and all that. Like you just cannot afford to delay at all. So some of these things that are happening because of COVID they're important, but there's a balance between what's the risk you're entailing, because of course certainly right now in Canada, most people don't have COVID when they come into the hospital. Right? But the trouble is that you can't know, and it's one of the challenges in stroke is that if someone's aphasic and they can't talk to you, or there's no family, or there's no one to tell you what's going on, you have to assume that they might have COVID, and that's a big challenge.
Well, otherwise, everything you're doing sounds very promising. And it was very interesting both to read about it and to hear about it from sort of the behind the scenes from you speaking about it. I know when I told our executive team, they got very excited that you were coming on. Your reputation definitely precedes you. So I'm sure they're all going to be listening in and are very excited to hear you talk about your research.
Okay. Great. Well, thanks for inviting me, and good luck. What are you?
I'm in my MSc Epi at U Ottawa, so I just started this September. So yeah, we're all online during this as well. But yeah,
wonderful. Well, good for you. Well, good luck.
Thank you very much.
I mean, it's probably I would say that the epidemiology training was looking back, it was the most important thing I did with a vision towards doing clinical research. Like just getting the methodology training was the single most important.
Yeah, even just learning how to write a protocol. That's what we're doing one of our classes right now, and I would have no idea where to start if it weren't for this. So yeah, it's definitely going to be very valuable. So I'm looking forward to the next couple of years of that. Should be good.
All right. Well, I wish you luck. Thanks very much for inviting me.
Thank you so much for joining us. Bye.
All right. Bye-bye now.
Thanks for tuning in, guys. Hope you enjoyed hearing a little bit more about a true icon and leader in stroke research. As always, don't forget to check us out on Instagram and Twitter at Behind the Numbers with no E in numbers, as well as follow and or subscribe to us on Spotify, Apple Podcasts, and YouTube. See you next Monday.